having seen CFD in action, where we are able to get a velocity field for the case of fully developed flow through a rectangular cross section duct. Now let us see what we need to do to make it more general and something which is also useful in practical context. Let us now discuss the course outline and what we are going to do as part of this course. We see that the first thing that we need for any CFD solution is the set of equations. We need to know what equations we want to solve, and we need to have a clear identification of the flow domain, and we also need to have the boundary conditions, and if we have an unsteady flow, we need to also have the initial conditions. So the first part, the first phase of a CFD solution is to have a mathematical description of the flow in terms of the equations which describe the relevant variation of the relevant parameters. These in fluid mechanics are none but the Navier-Stokes equations. So as part of this course, we will be first deriving the Navier-Stokes equations, for which we assume a first level course in fluid mechanics as a prerequisite, and maybe a school level mathematics should be sufficient. And once we derive the equations, then we get into a solution using an analytical method or the CFD approach. So then we come to the CFD approach, and we know that the CFD approach means that we have to identify the points at which the grid points at which we want to get the desired velocity variables and so on. So there is a lot of discretization of the flow domain is one of the steps. So instead of going through that particular route, what we do is that we will first make we will see that the solution of a fluid flow for the general case requires not the solution of a single equation, but a set of coupled equations. For example, typically we have 3 momentum equations and 1 continuity equation together, which have to be solved for the 4 variables of interest, which are the 3 velocity components and pressure. Now how to solve this together is a very complicated issue. So what we do is, first of all, we generate a template which gives us a satisfactory approximation, numerical approximation to a generic equation, partial differential equation, which describes the type of equation which we will have to repeatedly solve in fluid mechanics. So we will, at the end of the derivation of the equations which are needed for CFD, we come up with a generic form of a scalar transport equation, and for different values of diffusivities and source terms, we can show that this scalar equation can represent the momentum balance in the x direction or y direction or z direction or energy transport equation and all these things. So for this scalar transport equation, we derive a template which should give us a satisfactorily accurate solution without any convergence problems if implemented properly. So we generate the template for the solution of the generic scalar transport equation. Having established this, in the next module we look at how to use this template to solve the coupled equations which are necessary for the solution of all the equations which govern the fluid flow, that is all the 4 equations in the case of isothermal flow, maybe along with the energy equation, and maybe along with equations which represent turbulent flow and so on. So that kind of solution of coupled equations is going to be done in the next section. Now this will give us a framework for the solution of all the equations which govern fluid mechanics. Okay. Now we will try to make it more efficient. So we look at what methods that are available for the solution of the discretized algebraic equations, which when we consider general flow are typically nonlinear. So we have to come up with a solution of nonlinear coupled algebraic equations. So we look at those issues, and we look at the generation of the grid for an arbitrary 3-dimensional geometry. Okay, so not something which is as simple as a rectangle or a square for which we can describe the whole flow domain in a Cartesian coordinate system or a cylindrical coordinate system. If you have a body which is irregularly shaped, we still have to be able to discretize this into tiles in the case of 2 dimensions, such that all the tiles when put together will give you the overall thing. So there are some specific methods for a structured mesh generation or an unstructured mesh generation. Okay, so we look at these methods and then come up with algorithms which will enable us to discretize any arbitrary shaped domain, flow domain, into small tiles which when put together will give us the total area, the total volume. So this will be the next module, and finally we look at a solution procedure which will work not only with the rectangular coordinates, but also with this generally arbitrarily shaped arbitrarily shaped tiles, to be able, which will enable us to discretize the governing equations on these control volumes and then convert the partial differential equations into algebraic equations. Okay. Then whatever methods that we have developed in earlier modules for the solution of these algebraic equations can be used to get a solution to the general arbitrarily shaped flow domain involving fluid flow and all these things. And as a final module, we will look at more number of equations which represent the complexities of industrial flows. So that is, what we would have developed until this is necessarily for the Navier-Stokes equations, that is, which represent laminar flow for a Newtonian fluid. Okay. We will consider the possibility of turbulent flow, which is the most often the case in industrial things. We will also consider the energy equation when we have any kind of heat transfer. We will also extend the equation set to the case of chemical reactions, reacting flows, so that at the end of this module, the final module, we will have a set of equations which describe unsteady turbulent reacting flows, which can also be laminar, and for all this, for this kind of complex case, we have a set of equations. We will show that this set of equations has equations which can be put in the standard generic transport scalar transport form, for which we would have made by then a template. Okay. And so using the methods that we would have already covered in the earlier modules, we will have the capability to solve for generic unsteady turbulent reacting flow in a flow domain of arbitrary shape. So that will cover the basic set of techniques which will ultimately lead us to attempt solution for industrial flows or complicated flows. So the outline of the course is, having done the introduction, derive the equations, Navier-Stokes equations, which govern the flow of fluid, and extract from these equations a generic scalar transport equation form, and generate a template for the numerical solution of this generic scalar transport equation form using the principles that have been evolved as part of the CFD subject development, and use this capabilities to solve a single generic scalar transport equation to evolve methods for the solution of the coupled equations of the momentum and continuity, so that we have a complete solution procedure for the Navier-Stokes equations. And then we come into the domain of mathematics and the solution of algebraic equations, simultaneous algebraic equations, and we look at a variety of methods using which the discretized equations can be solved efficiently. And then we look at the practical case of having irregular shaped domains, fluid domains, in which we want to know the flow variables. So we look at methods for algorithms for a decomposition of the flow domain into small tails and small volumes, small bricks in such a way that we can discretize the whole domain systematically into small tiles, and then we finally develop the method by which even an arbitrarily shaped tile can be taken for the discretization of the equation. This is where we use the finite volume method. Okay. So, using these set of techniques we will be able to tackle real industrial flows. So, that is outline of the course, and the first part of this is the development of the equations. Let us now look at the equations which govern fluid flow. We are all familiar with these equations. These are nothing but the very same equations which govern also the solid mechanics. By this we mean the equation of mass conservation, the equation of momentum conservation, and the equation of energy conservation. So, these are the same equations which also describe the flow of a fluid. What is different between those, for example, the Newton's law of Newton's second law and the equations that we are going to derive, is that those equations are described for a system of particles, whereas in a fluid mechanics scenario we are interested not in a system of particles on which forces are acting, because of which the particles are the system is moving at a certain velocity in a certain direction, but we are interested in a specific domain in which things are happening. For example, we may be looking at a fluid flow involving a soup making reactor, in which you put different components of the soup, you mix them, you heat them, and then they cook and then they go out. So, we are not interested in a single soup particle or a banana or a pea or something like that which is going through this. We are looking at how different reactants are coming together into this domain and how they are exchanging heat with the surroundings and other sources and how they are going out. Okay, so, we are interested in a fixed domain, and within this domain we have to write equations which describe the inflow of reactants and outflow of products and so on. So, we distinguish this in the fluid mechanics community as a Lagrangian viewpoint versus Eulerian viewpoint. Lagrangian viewpoint typically refers to the system related equations like what we have in solid mechanics. The rate of change of momentum is equal to sum of all forces acting on the system of particles, whereas in an Eulerian frame of reference, in an Eulerian approach, we are looking at a control volume based derivation of the equations. Okay, so, there are in fluid mechanics literature we also have some theorems like the Reynolds transport theorem, which show the equivalence between a Lagrangian way of formulating the conservation equations and the Eulerian way of formulating the conservation equations. Slightly mathematical, given the viewpoint that this course, this particular CFD course, is intended for engineers whose mathematical skills we do not want to challenge too much. Okay. So, we would like to take a much more physically appealing route to the derivation of the governing equations. So, what we do is that we take a control volume, a brick with 6 sides, and we say that in this control volume we want to describe the mass conservation and we want to describe the momentum conservation or energy conservation, and then how do we describe it mathematically and how can we derive the corresponding equations which describe this. Okay, so, that is what our objective is. For example, when we talk about mass conservation, we say that we take a control volume, a 6-sided control volume, and we say that the mass conservation equation for the fluid within this control volume can be stated as the rate of accumulation of mass within this control volume is equal to rate of inflow of mass into this control volume minus rate of outflow of mass from the control volume plus any sources of mass. Now, most of the time we are not considering any nuclear reactions, and therefore, we say that there are no sources of mass itself, keeping in mind that this particular control volume will be ultimately made very small, so that the equation that we derive from this is applicable at almost every point within the flow domain. Okay, we are not saying that the point is infinite, is a point of infinitesimal volume, but it is so small a volume that at every point this conservation equation which we derive from this control volume analysis is applicable. So we can't think in real terms of sources of mass in a reactor, okay. So which are so small that they are applicable at every point. So we restrict ourselves to a mass conservation equation which can be stated like this: rate of accumulation of mass in the control volume, which I am abbreviating as CV, is equal to rate of inflow of mass into the control volume minus rate of outflow. I take this as a statement of mass conservation equation for a control volume, and I write these verbal statements into a corresponding mathematical expressions, and from that I derive the equation representing the mass conservation equation. So I can say that this is mass conservation. Okay, on the fluid in a control volume. Similarly, I can write a momentum conservation on the fluid in the control volume can be stated as rate of accumulation of momentum within the control volume is equal to rate of inflow of momentum minus rate of outflow of momentum plus other factors. We know that momentum can be changed by the application of forces. Okay, momentum can be changed by a rate of work done. So these are the kind of things that appear as plausible sources or sinks of momentum. Okay, and of these, given that we are looking at a control volume which is ultimately going to be reduced to a point which is prevalent in every part of the flow domain, we consider only forces, no work done by a turbine or a pump which is traditionally done in steady state energy balances and momentum balances in fluid mechanics. So we say that the rate of accumulation of momentum in the control volume is rate of inflow of momentum minus rate of outflow of momentum plus momentum changed due to external forces acting on it. On the control volume. Okay, so we can put net external forces acting on the control volume. So we say that a change in momentum within the control volume can take place because you have an excess of inflow or excess of outflow or you have some forces acting on it, and what these forces are something that we have to specify when we translate this verbal statement into a mathematical statement, and then from which we can get the equation. Similarly, we can write about the energy conservation and species conservation in the case of reacting flow, that we will see at a later stage, but right now we are concerned with these two statements and we will try to derive the corresponding equations from this. So for this, let us consider a control volume, and when we talk about a control volume, first of all let us be simplistic. Let us take a Cartesian coordinate system with x axis in this direction, y axis and z axis coming out to represent a right handed coordinate system, and for the sake of convenience, if this is our control volume, we have x, y, z, okay, the three directions, and you can see that this has 6 faces, this face, the left face, right face, bottom face, top face, front face, back face, there are 6 faces. So we assume that each of these faces, the bottom face or the front face or the left face like this, is aligned in a particular plane of the coordinate system. So that is why we have a rectangular shape in this, and then this is a control volume, and it has a length in the x direction of delta x, length in the y direction of delta y, length in the z direction as delta z, and we fix the origin here, and this origin is at x0, y0, z0, and for the sake of simplicity we assume that we have a stationary fixed coordinate system. Okay. So we want to write we want to describe the statement of the mass conservation on this control volume. Now this control volume is immersed within a large fluid domain. Okay. So and this is the basic control volume. It is like the discretized domain in our CFD, and many such bricks will compress together the flow domain. Okay. So we want to know what changes are taking place as fluid is flowing through and out of this control volume. Okay. So that is the description that we are looking at. So we have a fluid, and the fluid has a certain density rho. This is the Greek letter rho describing the density of the fluid, and so that the mass within this, the mass within the control volume can be given as rho times volume, and volume for this rectangular parallelepiped is rho times delta x, delta y, delta z. Okay. So now we can say rate of accumulation of mass within the control volume can be represented as variation with respect to time of the mass within the control volume will give us the rate of accumulation, rho times delta x, delta y, delta z. This particular term represents the left hand side of the mass conservation equation. Okay. So now this is, we are saying, is equal to rate of inflow of the fluid into the control volume and rate of outflow. Now when we talk about inflow and outflow, what we are saying is that there is a velocity field UVW, okay, representing the velocity components in the 3 directions, and this, because of this particular flow, because of velocity, then flow is coming through this space and then going out through this space, coming through this space and going out through this space. Okay. So in that sense we have to we can say that the faces, the surface of this control volume is the means by which fluid can either enter or leave the control volume, and if there is a net imbalance between the inflow and outflow, then there can be an accumulation. So the mass conservation equation is saying that the rate of accumulation is also equal to the rate of imbalance between the inflow and outflow. We have to evaluate the fluxes through each of the 6 phases. We can say that the flow rate through a particular phase can be seen as the velocity normal to the phase times the area of the particular phase. So since we have aligned the 6 phases of our control volume along the coordinate planes, if we take any particular phase, we can find out the area and multiply the velocity component which is normal to that particular phase in order to get the volumetric flow rate through that particular phase. So we can say that mass flow rate through any phase is equal to density times the velocity which is normal times the area of the phase. And by our choice of these phases which envelop the control volume to be aligned in the particular coordinate directions, this component velocity will be either u, v or w, which is specific to each phase, and this area here will be delta x delta y or delta y delta z or delta x delta z. Okay, so this is a simplification that we can achieve by choosing a control volume whose planes are enveloping planes are aligned with each flow direction. So now let us put some identifiers for these vertices. We can start with this origin here as point A here, this is B, C, D, and again E, F, G and H. We have already identified AB as being delta x and AE as being delta y and AD as being delta z. So these are the lengths associated with each of these, and the corresponding, for example, length EF is the same as AB, which is the same as CD, and similarly the AD is the same as BC as the same as FG, because we are considering a rectangular parallel pipette. So with this we can identify the inflow areas as the 3 phases corresponding to inflow rate through sides ADHE, bottom face ABCD, and the back face which is ABFE. Minus outflow rate through faces, the right face which is BCGF, the top face which is EFGH, and the front face which is CDHG. Okay, we are doing in a simplistic way here without worrying too much about mathematical rigor. Okay, in a in an intuitive way. So let us just take it like that. Therefore, we are identifying visually what is an inflow and what is an outflow, and associated with this inflow and outflow is the idea that there is a velocity component u is always associated in the positive x direction, and the velocity component v is always associated in the y direction, positive y direction, and the velocity component w associated always in the positive z direction. So if velocity is in the negative z direction, w has to have a negative value. For example, w of minus 20 meters per second is velocity going in the negative z direction. X of minus 15 meters per second is the velocity going in the negative z direction. So by the fact of associating UVW always with the positive coordinate frames, positive coordinate directions, we can identify an inflow and outflow from a visual identification of this. It can be done more rigorously mathematically. So through each phase we evaluate the mass flow rate by multiplying by the density and the velocity component, the appropriate normal velocity component, and the appropriate area of this particular phase. So for example, side ADHE, okay, so we can now evaluate these things. So this rate of accumulation of rho delta x delta y delta z is now through ADHE we have the velocity component is u, which is normal to this plane, so that is rho times u, and the magnitude of the area is delta y times delta z, delta y delta z, and all these are evaluated at x naught, where this is x naught, the origin is at x naught, y naught, z naught. Okay. So and the flow rate through ABCD, which is the bottom phase, will be rho times the velocity component, which is normal to this plane, is v, and the area of this is delta x times delta z, and this whole thing is evaluated at the bottom plane located at y0, okay, plus through the back face, which is ABFE, which is this one. So that is the normal velocity component to this is w, and the area is delta x times delta y, and these are evaluated at z0. Okay. So we can see when we talk about the mass flow rate being given by a velocity component, one of these three velocity components UW and one of these area components. For example, here we are taking u velocity and delta y delta z, and here we are taking v velocity and delta x delta z here, and w velocity like this. Okay. And each of these, the rho and u are evaluated for this particular thing at the center of this plane located at x naught, and similarly the rho and v appearing in this particular term are evaluated at the center of this particular plane, which is at y naught, x0 plus delta x by 2 and y0 z0 plus delta z by 2, like that. Okay. So these are the three inflow phases, and the outflow rate, mass flow rate through the three outgoing phases, so that is BCFG. So this is this. So this again is aligned in the positive x direction with an area of delta y times delta z, and the velocity component is u, which is normal to this. So minus rho u delta y delta z. Now this is evaluated at x naught plus delta x, because this plane has a centroid which has a coordinate length of x naught plus this delta x here. Okay. Now through the second phase, which is EFGH, the top phase here, and the velocity component normal to this is the v velocity. So we say minus rho v, the area is delta x delta z, and this is located at y naught plus delta y, and the final face is CDHG, which is that front face. So, the velocity component rho w times the area, which is delta x delta y, centered at z naught plus delta z. Okay. So, these three represent the mass flow rates through the three surfaces identified as outflow, and these represents the mass flow rate through each of the three faces identified as the inflow faces. So, this equation, this verbal statement of mass conservation is now represented mathematically like this. This is an equation, now it has become a mathematical equation. We can do all allowable mathematical operations. So, what we do is that we divide each of these terms by the volume, okay, divide by delta x, delta y, delta z, the product of this. So, this is equal to volume, and take limit as delta x tends to 0, delta y tends to 0, and delta z tends to 0 as appropriate. Okay. So, if we do these things, divide by delta y, delta x, delta y, delta z, and take limit as delta x, delta y, delta z individually tend to 0, okay, then we get an interesting equation. For example, if we take the first term here and divide by delta x, delta y, delta z, this cancels out and we get d rho by dt. Okay. So, the first term becomes d rho by dt, and in this we have to divide each of them by delta x, delta y, delta z. We will take a combination and put them together. We take this one here and the corresponding thing at x plus delta x, this term here, and then we take them together. We divide these two terms by delta x, delta y times delta z, so that this and this cancel out, and we get rho u at x naught minus rho u at x naught plus delta x divided by delta x from these things. Now, let us take this term at y naught and this term at y naught plus delta y together, divide by delta x, delta y, delta z. So, delta x cancels out, delta z cancels out, and what we are left with is plus rho v at y naught minus rho v at y naught plus delta y divided by delta y, and we take the remaining two terms together, c and c. If we divide these terms by delta x, delta y, delta z, then delta x, delta y cancel out, and we will have plus rho w at z naught minus rho w at z naught plus delta z divided by delta z. Okay. So, by dividing this equation, each term in this equation by delta x, delta y, delta z, then we have this, and we take the limit as delta x and delta y, delta z tend to 0. So, there is no delta x here. Here we have delta x coming here. So, limit as delta x tends to 0, and here delta y appears. So, limit as delta y tends to 0, and here delta z appears. So, limit as delta z tends to 0. Okay. Now, we can see some derivatives appearing here. So, we can say erase this. We can see that limit as delta x tends to 0, rho u at x naught minus rho u at x naught plus delta x divided by delta x. If we consider this term, limit as delta x tends to 0, rho u at x naught minus rho u at x naught plus delta x, this whole thing divided by delta x is nothing but minus d by dx of rho u evaluated at x naught, okay, by the definition. By the definition of a derivative, partial derivative of rho u with respect to x is given by this with a minus sign, because we are doing x naught and x minus del x naught. So using this definition we can write this equation as partial of rho with respect to x as with respect to t as minus partial derivative with respect to x of rho u at x naught, and we should remember that this is for the control volume centered at x naught, y naught, z naught, okay, roughly. So we can do this, and minus the second term here is nothing but partial derivative with respect to y of rho v and the next term will be partial derivative with respect to z of rho w. Okay, so we can put this together and say that d rho by dt, and we can bring this to the left hand side, plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w equal to 0, as being a mathematical statement of the mass conservation equation for a fluid, which is applicable in the limit as delta x and delta y delta z tend to 0, which is as we approach a particular point. Okay. So this is a mass conservation equation which is now appearing in the form of a partial differential equation involving time and the 3 spatial directions, okay, as the spatial derivatives as the independent variables. So now the density as well as UVW from this equation can be a function of xyzt. In the special case where we are dealing with an incompressible flow, then rho is not a function of, rho is not variable, then we can say that this thing goes to 0 and the rho is constant. So we can take this out of the derivatives, and since the right hand side is 0, this equation reduces to the simpler form of dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0, or del dot v equal to 0. This is also known as the continuity equation, and in the more general case we have del dot rho v equal to 0. This is the continuity equation. Okay, so the variation of UVW and rho, which are the properties of the fluid and the flow at any point within the flow domain, must be such that they satisfy this equation, because it is a fundamental statement of the mass conservation equation. So this is one of the equations which describe the variation, how the flow properties can change in a particular control volume. We can, this is one equation, and we can also apply the other fundamental equation that we know. This is the momentum conservation. So whatever be the fluid flow, it has to obey the mass conservation and momentum conservation as well as the energy conservation equation. So let us now take a very brief look at the momentum conservation. We have already written a statement on that. So let us just momentum conservation can be written as rate of accumulation of, instead of mass we will say momentum is equal to rate of inflow of momentum plus rate of outflow of momentum plus net external forces acting on it. Acting on the control volume. We say that if there is a force and it is acting on a control volume, that it introduces a rate of change of momentum which leads to a rate of accumulation of momentum. So, that is what we are saying here, and this can be written developed analogously like this. We can make advantage of what we have already derived and modify this slightly. We note the fact that momentum is a vector quantity unlike mass. So, this equation has 3 components, and in each of the 3 components this equation is valid. So, we can say that rate of accumulation of momentum in the x direction, so which we call as x momentum, is equal to rate of inflow of x momentum and rate of outflow of x momentum plus net external forces acting on the control volume in the x direction. Okay. Similarly, we can say that will be the x momentum conservation, and similarly we can write the y momentum conservation, which is a shorthand notation for saying that conservation of momentum in the y direction. Okay. Can be stated as rate of accumulation of momentum in the y direction is equal to rate of inflow of y momentum minus rate of outflow of y momentum plus sum of all external forces acting in the y direction. Okay, so, this can be a statement of the conservation of momentum in the y direction, and similarly conservation of momentum in the z direction. So, using the same procedure as what we have adapted for the mass conservation, we can convert this verbal statement into a mathematical expression by essentially following the same way. Rate of the total x momentum, we know that momentum is mass times velocity. Okay. And we know that the total mass in this is rho times delta x, delta y, delta z times v. Okay. Now, we can say that momentum in the x direction is, which we are calling as x momentum, is velocity component in the x direction. So, this will become rho times delta x, delta y, delta z times velocity in the x direction, which is nothing but u. So, that is rho delta x, delta y, delta z times u is the momentum in the x direction contained in the control volume. So, we can say rate of accumulation of x momentum in the control volume is nothing but rho times this times the velocity component u, is the inflow rate of x momentum through the sides. The flow is coming in, so whatever it has it brings in the enthalpy, it brings in the entropy, it brings in x momentum, y momentum, z momentum. So, whatever it is, it brings in a concentration of a particular species. Because we are considering a flowing system, there is a convection or advection component associated with the rate of change term, and that is what is being described in this. And outflow rate of x momentum plus the sum of all external forces acting in the x direction. So this is a statement of the x momentum conservation. Okay, so now we can do it in the same way. Dou by dou t of rho times u times this is equal to, we have already evaluated the flow rate through each of the phases, and so just as we have defined x momentum as this, x momentum flow rate is mass flow rate times the velocity in the x direction. So the x momentum that is being carried by the fluid which is entering through the left phase, which is this, is u. So we can put u here, and the x momentum being carried by the fluid which is entering through the bottom phase is mass flow rate times the velocity component in that particular direction in representing the x momentum, which is u, and the x momentum being carried by the fluid which is entering through the back phase is the mass flow rate times the velocity component in the x direction. And again here this is the mass flow rate leaving the control volume through the x phase, so multiplied by the u component will give us the rate of x momentum flow rate through that particular out phase, and rate of x momentum flow rate through the top phase will be the mass flow rate through that particular phase times u at that particular phase, and the mass flow rate leaving through the front phase will be the mass flow rate through that, the momentum flow rate, x momentum flow rate will be the mass flow rate times the x momentum velocity component, which is u. Okay. Now we have external forces acting on it. So we'll, for the time being, we'll just put it as sigma f external acting in the x direction. We will not right now talk about it, but we can, just as we have done earlier by dividing delta x, delta y, delta z and all these things, we can write this term as dou by dou t of rho u here, and clubbing these two like earlier, we will have rho u square at x naught minus rho u square at x naught plus delta x, and here you have u and v here. So we have already u, v, so rho vu at y naught minus rho vu at y naught plus delta y, and here we have rho wu at z naught and rho wu at z naught plus sum of all external forces acting in the x direction divided by delta x, delta y, delta z times limit as delta x tends to 0, delta y tends to 0, delta z tends to 0. Okay, so this is a statement, and using the same argument as earlier, we can derive a mathematical expression which is d by dt of rho u plus dou by dou x of rho u square plus dou by dou y of rho u v plus dou by dou z of rho u w equal to sum of all external forces acting in the x direction, the component in the x direction, divided by the volume delta x, delta y, delta z, in the limit as delta x tends to 0 and delta y tends to 0, delta z tends to 0. Okay, so this is the x momentum equation. We can also derive the y momentum equation, all these things. What we see here is that we still have the UVW components coming in this. This statement is not complete until we describe what these external forces are. Okay, so the derivation, in order to complete a statement of the momentum conservation, we have to describe what these external forces are, and we will consider that in the next class.